Oh! Oh look, it's just a human guy. Wow. First student. First student. You're here early? Oh. Trying to be deep as that, huh? Yeah. Possibly. Possibly. Only. Oh, wow! Check that out! Just a human guy redeems teacher's pet, probably using all of their channel points. Amazing. What an event. What an event. They just thought of it on their own, without any encouragement from outside. Amazing. That's what I like about teachers' pets. They're just self-motivated. They're the best students. Just like just a human guy. Oh, what's up, Guru? What's going on? Oh my, okay. Okay, is that all it takes these days? Just one emote to get a shout out? Alright, here's Prof. Melko's shout out. Where is it? Hey, folks. All 10 of you. Go check out Melko. All 10 of you. Click the follow button. That's right, that's right. Yeah, definitely, most def. Most def. That's right. I'm right. Yeah. Yep. One of my many original ideas. The feeder of chickens, Guru. That is right. That's Professor Melko. Prof. Melko is the first Twitch professor to be on top of the chicken stream. That's right. Master Brander. You see these emotes that you see floating around? Like this toxic one? That's how Prof. Melko works, you know? Master Brander. Wait, is that Fauci? Wait, is that a Fauci? What? Dude. That's master of Twitch right there. Look at that. Look at that. That's amazing. was enough calc, I'd say. At least the basic principles, yeah. Might not remember what the antiderivative of 1 over 1 plus x squared is. Who cares about that? Alright, let's see. Oh my god. Is my... I hope my pencil is charged. Jeez. Oh, I should have checked this. What's my pencil like? Oh! 80%. 80%. Alright. Let's get going, folks. All right. Your new homework assignment is up. It's due on Saturday. Did I write that? Let me write that, folks. One homework assignment. All right. We're going to be starting the sequences and series part of the class here soon. Don't compare with other classes. They might be doing some other things right now. I decided to punt on that because this material that I decided to focus on first is much harder. And I would rather spend more time on the harder material than just cram a bunch of random stuff in. So, we might get back to that stuff at the end. That's what's happening in comparison to other classes. What will be on the exam today? Integration techniques, smattering, not so many. It's not that many problems. Integration techniques and improper integration. Those two things. All right, I'm like 75% of the way done constructing the exam. So right after class, I'll finish the exam and I'll put it up. It's at 2. It'll become available at 2. All right, so have fun with that. Okay. Oh, thanks for following T-Cabmo. Thank you. All right, good. Let's begin. We're gonna begin a new topic, folks. New topic. It's called Taylor Polynomials. It's a fascinating topic. It's really wonderful. It's a wonderful new topic. Every time a new topic shows up in a math class, you should situate it in the tree of knowledge. What's the underlying story behind this new concept? All right? What's going on with my collar? Okay. What's the underlying story? Okay. Let me I'm here. What's this garbage? Anyway. Okay. What's the story? I'm going to tell you a story. I'm going to tell you the story that's behind Taylor polynomials, so that I don't get annoying students saying, hey, what's the point of all this? Okay, I'm going to tell you the point first. All right, this is a story. It's a story time. Okay. I've been teaching for what? 10 years now? I've been teaching for 10 years. I've been teaching for 10 years. For long enough. I start to notice some patterns. Okay? So here's what my students are like. Okay, here's what my students are like. Okay? Whenever a problem involves polynomials, what's a polynomial? Like this. Like that. Or maybe it's secretly a polynomial if you just foiled it out. You know, like. Whatever. Anything like this, polynomial math, students are happy. So here's this picture of a little student. Here's a student. I like math. Okay? Okay? Like, ask yourself, hey, does that sound like me? Trust me, it does. Alright? You're gonna be happy. Every time the math problem just has a polynomial in it. Oh, you want me to add 2 of them? I did that in 8th grade note card. You just add like terms. Oh, you want to differentiate that? Power rule. Done. Oh, you want me to multiply 2 of these? Oh, FOIL. FOIL. Easy. Just do some FOIL. You want me to integrate these? Easy. Anti-power rule. Polynomials? Good news. I like math class. And then I noticed the following pattern. I noticed everything else you get this. Oh no! Where's my note card? Yeah? What's in here? Sine, cosine, everything. Sine, cosine, trig, ln, all this stuff. Like half of you probably still don't know what arctangent looks like. Even though I did it in office hours, I showed you stuff. Or I sketched it. Yeah? Oh, everything else sucks. Just, oh no! How do I deal with it? What's sine of 2x? What? What the heck? What is that? Yeah? Everything else causes much distress. This is what my students are like. Yeah? Okay. So, what I'm going to share with you is a way... Students have a dream. Students dream. Let's state a dream. Students dream. I wish everything were a polynomial. Okay, here's your dream. Okay, so now I'm going to tell you what is a Taylor polynomial. It's how you make that dream come true. All right? At least as much as we possibly can. Okay, so I'm going to tell you one fact of life, students. Everything else is necessary, and not everything is a polynomial. That's true. Not everything is a polynomial. So you're not going to get your dream, but mathematicians have fought the good fight. And they have come up with an amazing method for trying to create something that takes a complicated function that you don't like, that you have not studied enough of, I guarantee. They take that thing and they try their best to make it look like a polynomial. Try to find the best polynomial for each of these crazy functions you don't like. That's the story of Taylor polynomial. Right? So that's the story of where Taylor polynomials come in. Because it turns out, students, that you're not the only person that has this aesthetic. That polynomials are simple things, everything else is complicated. You're not the only one that noticed that. Great mathematicians before us noticed that, and they tried their best to put everything, to try to approximate everything using polynomials. That's what they tried, and the person who popularized this first is a person named Taylor. Okay? So we're gonna learn this. We're gonna learn this magic approximation method. We're gonna learn this week. We learned this. Okay? I'm gonna start with an example. All right. No, it turns out is actually a wonderful phrase, because without saying things like it turns out, a student is constantly lost, can be constantly lost because they don't know the end goal. So it turns out, great phrase. Okay, so here we go. Now, let's put up one of the worst, the functions that students still have to memorize properties of, they don't understand fully. Sine. Okay, I tried to draw it best I can. And let's focus at a particular point. So step one. Focus on a particular point on this graph. Like, let's take the origin. That's a good point. And you look at this sine graph near the origin, it's all, it's like a bumpy hill of some sort. Well, you can ask the following question. Question number one. Which linear function looks most like sine at that point? Which line? Line means linear function. Linear polynomial. Linear function, degree 1 polynomial. We could ask this question. Which line fits sine x the best? The answer, the class should answer unanimously. The answer is, of course, the tangent line. That's clearly the line that tries its best to be a random, complicated, curvy function. For us, the tangent line can be computed thanks to knowing the derivative. Oh. This curve, y equals x. The derivative of sine x is cosine x, and you plug in x equals 0, you get 1. So it's a slope 1 line that goes through the origin, so it's y equals x. This here is the best line that approximates this function. Okay? Awesome. So, if we asked to focus on other points, like x equals a, the question of which line best approximates this graph, that line will change, of course. This answer will change. But you can write down all of the answers at once using this formula of linear approximation from Calc 1. You can write them all down. They turn out to be y equals output at A plus, all right, in general, it's output plus the first derivative times x minus a. It's like a point slope form for the tangent line, equation of the tangent line of f of x, of y equals f of x at the point x equals a. This is the, I don't know what it's called, point slope form of equation of tangent line. Approximation of y equals f of x at some other point of concern. It's going to be some downward pointing line. But what's its equation? That formula tells you. All right? So this is how you do it. Okay, so passage from complicated function to tangent line is version number 1 of this grand Taylor polynomial dream. So this dotted arrow, you already know one version of it. It's called replacing a function with its tangent line. You already learned that. So now we're gonna do something fancier than that. Okay. Now we do something fancier. We just make this, we generalize this procedure. Why did we fix only lines? What if we asked ourselves, hey, is there a parabola that best fits this or that function at a point? Is there a cubic equation that best fits this or that function at a given point? Is there a best fit polynomial of a given degree? Is there a polynomial, a degree D polynomial, of best fit? Okay, and remember the context. Context is you're looking at a function at a particular point. At a particular point. So I'll show you another example. I'll show you another example where I do parabolas. Parabolas. Students, you know, if I ask them, hey, do you know anything about y equals e to the x? Oh my god, that's so complicated. Yeah, well, here, I'll try to sketch the graph. Even sketching the graph, like, how do you know you got it right? It's so complicated. It's so transcendental. It's inaccessible to finite minds. Oh yeah, it's okay, boom, yeah. Okay, something like that, yeah, e to the x. Let's concentrate at x equals 0 again. Okay, so you have this function. Okay. What I'm gonna write for you is the parabola which fits this function best at that point. Not a line anymore, parabola. For e to the x at x equals 0 is, I'm gonna write it for you. I'm just gonna pull it out of nowhere. first. It is 1 plus x squared over 2. Y equals this. Now I'm going to try to explain visually what's going on here. Okay, this is going to be a difficult thing to explain without face-to-face in an online non-face-to-face class. Let me show you what I mean. Take all the parabolas you can imagine. All right, so some of them are wide, some of them are skinny, right? Some of them are upside down. Yeah, there's all kinds of parabolas in the world. Okay, but you only get to play with parabolas. Now you take a parabola and you try to find one which stays with the graph as much as possible. Okay, so let's think about that. Let's zoom in here. Zoom in here. Zoom in. You're gonna have some shape. This is the complicated shape. And here's the point that we're concentrated at. X equals 0, y equals 1. Okay? Now, there will be several parabolas which are merely going in the same direction as this curve. What does that mean? If you sprout off the tangent line, there will actually be many, many parabolas that go that direction at that point. I'll try to draw a couple, but you should try to draw more, like on your own. Look, I'll try to draw a couple. I'll try my best. Here's one. It's just at that moment it's going the right way. But you can have another one. Wider. But the vertex, the bottom point of these two parabolas is different. Like this one has vertex way out here, this one has vertex here. There's actually an infinite family of parabolas that are going the right direction at that point, that have the right tangent line data at that point. But there's actually one which spends the most amount of time, so to speak, intuitively with the function. There's one magical one. So there are infinitely many which share the same tangent line. But there's only one which shares the concavity. Concavity is a second order measurement of curvature, of like how much a thing is, which direction is a thing going. What is concavity? Concavity is the second derivative. So out of all these parabolas, there is exactly one which has the same second derivative as the complicated function at this point. That parabola is the second Taylor polynomial. This magic parabola is the second Taylor approximation, Taylor polynomial approximation. Of our nasty complicated function. So let's go back to this example and I'll show you why. Why does it have to be this one? Why is this the parabola that matches both the first derivative, has the same direction, and the second derivative? Why must it be this one? So let's go write this down. Versus and at the point. We're gonna versus these two. Students hate the right-hand side. Students love the left-hand side. But I want to show you why the parabola on the left-hand side is really good for the right-hand side. Take the one on the left and see. What is the first derivative? Or slope at x equals 0. Okay, let's do that. How do you take derivative? It's just a polynomial. It's our dream situation. Ah, done. Easy. Slope is derivative equals 1 plus x. And derivative at x equals 0. I have a point I'm concentrating at. You get 1. Okay, now go on to the right-hand side. Right-hand side. Oh boy, what is this thing's derivative? Oh, that's e to the x. The derivative. dy dx equals e to the x again. It's a funny joke. It's a joke thing. The end of the punchline of many jokes in math. Okay, at x equals 0, I have a point I'm concentrating at. I get e to the 0, which is 1. Oh, nice. What did we conclude? This here parabola has the same slope as the complicated function. That's a good start. Why would you ever consider a parabola that's going a completely other way? That's not a parabola of best fit. No, no, no. At least go the same direction. But now I'm going to show you the subtle extra layer of goodness of this left side parabola. Okay, next. Compare concavity. By concavity, I mean double prime. Okay, so we take this parabola and we take its second derivative. Conveniently, I've already computed its derivative. And so its second derivative well, 1. Okay, cool, not bad. Notice how it was really convenient that I had a 2 here. If I didn't have a 2 there, then this 1 wouldn't be a 1. It would be something else. But let's look at what happens on the right-hand side. Let's take the second derivative. Or f double prime. And at x at x equals 0. Our point of concentration. Oh, let's look at that. F double prime is, oh, very funny, e to the x again. That's nice. All the derivatives of this right-hand function are very, very easy to write down. There's a pattern to them. That's a good thing. Okay, so let's write this down. At x equals 0. Whoa! Nice! But like second order. This was a first order. And even before that, the output at x equals 0. So even before, let me go even before. If you look at output at x equals 0, you get 1 on the left-hand side, and you get the same output too. So the parabola isn't just floating off somewhere else in space, up and down or whatever. It's actually going through the same xy point. It's going at the same direction, and it's sharing the same concavity, the curviness of the original graph, the second order. Okay, so this is the parabola that hugs the e to the x graph a little bit better. By a little bit better, we specifically mean that the second order information matches up, that the concavity is matching up to be precisely the same on both sides. Okay? So that's why there is a parabola of best fit. So that explains what we mean by parabola of best fit. Means outputs match, first derivatives match, and second derivative matches. If all three of these are checked, you have the parabola of best fit, and here's the miracle. In all the functions we ever consider in this class, there will be a parabola of best fit. And to find it, right now all we have is a puzzle. You have to just match a bunch of numbers. But I'll eventually show you a formula that finds this parabola of best fit. A formula that's going to be endless in a sense. Okay? This parabola of best fit is called the second Taylor polynomial of the function at x equals a. If we were looking somewhere else, we could play the same game. All right? Which one of these do the calculators use with the line of best fit? Oh, okay. There's another situation, D-boy, where you have the phrase best fit. In fact, it's in that other situation where you see the phrase best fit. I'm just using the phrase best fit because I'm teaching you sort of the role that these Taylor polynomials are playing. They're trying to be the complicated function for the longest period of for more than the other functions are being with the complicated function. It's fitting better. That's all I mean. But in the phrase best fit is also used, B-boy, when you have like a bunch of data and you find there's like oftentimes, I mean, there's always some line which fits the data best among all the lines. It minimizes a bunch of errors that you can look up from this situation. Okay? So that phrase line of best fit is not the same as how I'm using it. I'm using it as follows. You have some complicated curvy shape, all right? And you're only allowed lines. Someone says, I can only deal with lines, folks. I'm so bad at math, I can only understand lines. Well then, if you have this point on this curvy shape, which line best represents that curvy complicated thing at that point? Well, it's gonna be this line. The tangent line. Okay, maybe someone is a little bit more fluent with math and can handle parabolas. You could ask, which parabola is that curve most like at that point? Is there a parabola that this curve looks the most like? There is. It's the second Taylor polynomial of this curve at that point. And it's some magic one parabola, degree 2 equation, that looks the most like this function at that point. And the story continues forever. Is there a best fit cubic polynomial at this point? Is there a best matching degree 4 polynomial, etc.? The list of these polynomials is the list of Taylor polynomials. So the questions continue. In a natural way, is there a best looking degree n polynomial? A most appropriate, a best approximation, if you want to use that phrase. Is there a best looking degree n polynomial which approximates a complicated scary function that you don't like, for example, at a point x equals a? Is there always one? The answer in our class, for the functions we care about, there's like some adjective, but for the functions we care about, the answer is yes. For us, our functions we ever consider, the answer is yes. And it's called the Nth Taylor Polynomial. At x equals a. All right? Yes, B-boy. To find the tangent line, you need to know the derivative of the function. Okay? So, in order to find these Taylor polynomials, B-boy, for reminding me of this thing, to find the first Taylor polynomial, which is the same as the equation of the tangent line, you're gonna need to compute the derivative, B-boy. Correct. You'll need to know the slope. At that point, B-boy, 100%. I'm just gonna keep writing now. To find the second Taylor polynomial, as an ingredient, you're gonna have to find the second derivative. Not just the first, but also the second. The parabola needs to be going in the right direction and have the right concavity at that point. So you're gonna have to compute these two. I will let you fill in the rest of the pattern. Homework assignment. Fill in the rest of this pattern. B-boy. This is just for B-boy. Okay? I want you to do it right now. See if you can say what the next sentence is in this list of how to compute the nth, what ingredients you'll need for the nth Taylor polynomials. Awesome. Okay. So now, B-boy, I'll let you do that. And now what I'll do? Okay, so now what I'll do is I will show you the general computational method or the formula for this Taylor polynomial, best fit polynomial of degree n for any given function at any given point. So the general formula. Then if you want your note cards, oh wow, yeah, B-boy, you're ahead of me. If so here's a question that B-boy is suggesting. Hold on. So for every given degree, linear, quadratic, degree 3, degree 4, 5, if there's always a best fit polynomial, a polynomial that's the most appropriate replacement for your given complicated function, the most appropriate replacement, why not just crank it up to infinite degree? Is there such a thing as an infinite degree polynomial? A good question. We will explore that later in the course. In fact, that's one of the main things we're going to sort of try to understand. Is there such a thing as an infinite degree polynomial? And can we manipulate them like we do ordinary polynomials? That would be like a massive life hack which changes a complicated function to something that's, sure, infinitely long, but at least it's only a polynomial. Great, B-boy. Keep thinking that way. Right now, just finite though. Let's deal with actual polynomials. General formula. Note cards ready. Suppose f of x is a function, and by function, I mean the types of functions we see in class. Sine, cosine, all these, tangent, all of them. It's very hard in our class to get out of the realm of functions where this formula doesn't apply. Just whatever. Suppose f of x is a function, like the ones we deal with. And x equals a is a point you're interested in. All right? I'm going to write for you the general formula for the nth degree Taylor polynomial. Notice how long this phrase is. Let's just give it a name, yeah? T sub n. Let's be fancy. Let's put names. T sub n. The nth degree Taylor polynomial is... Here we go. Start off with the output of the function. So plug in a into the function. That's a number. Put that number there. Then add. Next, take the first derivative of the function and see what it is at a. Take the slope. And then multiply by x minus a. Notice that at this stage, this is simply the linear approximation of the function at the point a. It starts off like that, and then it continues. You take the second derivative. And for reasons, you divide by 2. And I don't know why I put a factorial there, but 2 is 2 factorial. So I'm just going to keep it there. X minus a all squared. Boom. Put that there. Next, take the triple derivative. And instead of dividing by 2 factorial, divide by 3 factorial. And so on. Up until the nth derivative. All right, so I want to focus on some pieces of this formula. Just as a formula right now, these are all numbers. These are numbers that you'll need to compute. A is, of course, a number that's given to you. When we write f to the round bracket n, this is just how we say nth derivative. And notice we're plugging in x equals a everywhere. That's why these are numbers. So you're gonna have to compute all the n derivatives at the point A, plug them in, and divide by more and more each time. Like divide by 2 factorial here, which is just 2 times 1. Divide by 3 factorial here, which is 3 times 2 times 1. Divide by 4 factorial here, which is 4 times 3 times 2 times 1, etc. You need to divide that out of the appropriate nth power. And then please pay attention. These powers of x minus a are increasing with the number of derivatives and this factorial. That's the pattern in this formula. All right, so this n is the same as that, the same as that. Why do I talk about this? Because I've been doing this for ages, unlike this Suleiman guy. All right? I know what the students have difficulty remembering, how they want. Yes, I'm giving you ways of remembering this formula. Okay, so awesome. This tells you how to find the polynomial, the dream polynomial that your complicated function is trying its best to be. Or the other way to say it. Among all the polynomials of degree n, which one is most like your function? This one. The one that's at the end of this horrible list of iterated derivative calculations. Okay, so what we'll do next time, of course, we'll compute a bunch of Taylor polynomials. And then graph them using third eye. All right, so that's coming up on Wednesday. We'll just compute these best fit dream polynomials. Our best attempt at making your dream come true, student, and many mathematicians before you. We will see what these best fit polynomials look like, and you'll agree that they are the best fit polynomials. They're pretty damn good. So that's what we'll do on Wednesday, and then we'll try to understand how damn good they are on Friday. We'll try to understand the error between a Taylor approximation and the actual function. That'll be more complicated to talk about, but that's the plan for this week. Okay. Okay, so let me now look at the comments. Oh, we have the standard very smart people in the chat. Good. Awesome. I never know the end goal. Exactly. Okay. Okay. Does this follow a series, or are people just randomly asking questions? I don't know. I mean, I hope you saw a pattern. B-Boy saw a pattern in the questions. Okay. All right, good. It's a you can Tika BAMO. You can find out about me in my personal website. Go check it out. How far in the sum should it be before this results in something negligible? Very good question, B-Boy. B-Boy has great questions. How good isn't... If someone says they have an approximation, you should always ask, oh yeah? What does that even mean? How good is your approximation? How do you measure how good an approximation is? Or for how long is your approximation valid for? Is it like good for longer and longer periods of time? Or is it only good in a little region? All great questions, B-Boy, and that's what the class is. That's one big theme in the class in Calc 2. Wonderful questions. Okay, so you need recorder, you need twisted cubic. Okay, well, twisted cubic is requested by a great mathematician among us. Smash Time Fools. Smash Time Fools is an awesome mathematician. Don't let the name deceive you. And a long age-old friend. So here, hey, Smash Time. You see the twisted cubic there? I know it's not a fractal, so you might not be able to see this properly. I know that that's what you do, so I apologize, it's not a fractal, but it's there. Smash Time. Okay, next, recorder. Recorder. Okay, Battling Storm. What does Battling Storm want? Battling Storm wants recorder and juggling. So, something you can play. Okay. What can I play, folks? That was good. It went. The recorder has a natural range that you can't go below, and I started too low. Happens to the best of us. Okay, so you want. Okay, so yeah, but class, think about this marvelous thing. Think about this dream. Isn't it cool that we can actually make a polynomial? There's a magic polynomial that best represents a given function at a given point. That's great news. That should bring a smile to your face. Because I know you. I've been hearing your complaints for many years now. This is great news, folks. And we're gonna sort of become masters at computing these things on Wednesday. And then we'll ask more subtle questions like, how good is the approximation on Friday? Well, I'll answer that. Provide some kind of answer. Awesome. Here you go. Here's your juggling. Okay. All right. All right. I had to get a PDF of the exam. Okay, let's get out of here. Back till the heart explodes. I'll do that next time. 27 lines, Shungite. Okay. Tika, since you're new here, here's some Shungite. It will help you combat the 5G radiation that might be in your life. So I'm going to give you 3 Shungite swirls. Put your face close. Put your face close to the screen. Okay, ready? Here, 1, 2, 3. I hope that was in the right direction. Okay, 27 lines. All right. I got a cubic surface in the mail the other day, and you notice, you see those lines? This is a cubic surface. Look closely. You will see that it has exactly 27 lines. Now, I will tell you something. I tried to count them with my own eyeballs. I only saw 26. I can't count. But there's 27. Yeah, but the last one, it can't just be 26, because they would come in complex conjugate pairs. So I can't count. Like I rotate the object and then I lose track of which lines I actually pointed at earlier and which ones I didn't. And I've never successfully counted all 27 with my eyes. So I'm still trying. I'm working on it, class. I'm working on it right now. I'm gonna try it right now again. Okay, class? Paint them in different colors. I don't wanna, it's white. I don't wanna mess it up. You know? I like it. I don't wanna mark it. So yeah, I got scumazed for sure. Unfold it and count. Yeah, I could. It's not like a piece of cloth, B-boy. It's made out of like some hard thing. It's not paper. But I wish I could do that. You know what? Why didn't I think of that, B-boy? Why didn't I think of that? Yeah. I really should have unfolded it. Okay, students, I gotta get out of here. I gotta make you the rest of your exam. It's almost done. It'll appear at 2 p.m. Students, 2. So get ready for that. Integration techniques and improper integrals. That's what I'll do. All right. Yeah, I am slacking. I got a lot on my plate. Like literally, I need to eat now. So I'll go put on the outro scene and let all your smart comments out at this point. Let out all the smart things you have to say. I know you all are you all would have come up with Taylor polynomials before Taylor. I know that. And everything's obvious to all of you. Because, I mean, you would have discovered it yourselves. So just let it all out. Let it all hang out. how obvious all of this is. That's a good contribution. That's a good place to start. Good place to start. Can you, oh, B-Boy, you won't be able to avoid diverging things, B-Boy. Not really. But what you will be able to avoid sometimes is impossible integrals. You can sort of hack your way around them by swapping over to the infinite Taylor polynomial, B-Boy. This is just words. Don't worry. We'll see some examples one day, hopefully. You can use it to hack certain problems, yes, but not the ones that you're thinking of. At least not the way I'm thinking of it. All right. All right, let's get out of here, folks. There are 30 of you here. Go home. And go invent all the trivial things that we learn. Go invent them for the first time. All right, and then come back and tell me you're smart. All right, see you guys later. Yep.